Oh, you're taking 18? Oh, man, yeah, I take 16. Yeah, new chapter.
I barely know.
In the story.
Yeah, but I still barely know.
Right now.
Also, from one side.
No, I heard you. About the same. Or, it's not the same.
Hi, how are you?
Good.
You didn't want to be in the same one as me. My kids just. She called me a rat.
It's as an intern. No, not much. What's going on with you? I'm feeling pretty good.
You could sit on this one, or you could grab another chair outside.
I can see that. So I have to take years. The power. No, I have. It's okay. So yeah. Okay. It was just upon you. Yeah. Okay. Did you like the work? Did you like the work? Or like doing college? I did a lot. I'm sure. Yeah. Where you want to come back? Oh, really? Great job. Sure. Yeah. I don't know what yeah. I am. Yeah. What's that? Oh, nice. I'll take this.
All right, everyone, let's get started now. Owen, let's get started. Okay. So I'd like to welcome you again to EE 300-3540. I hope that you had a moment to look at the syllabus, which I uploaded to Canvas. Today we'll go over that, and I'd like really to introduce for you the course to get you more interested into the topics, and hopefully you will have really a good semester. So this is the first course in power systems. I'd like to know who's interested in having a career in power systems, transmission, distribution, generation, controls. So who's just taking the course to fulfill certain requirements for graduation? Okay, that's still fine. Yeah, this is totally fine. I understand. I took many courses just to graduate, so. Well, it will be much better if you have some interest in the topics, but anyhow, we'll get into most of it into the fundamentals. I just need to check if Springfield people or people online can hear me. Can anyone confirm?
Yes, I can hear you. I'm from Springfield.
Okay, great. So let's go over the syllabus now to get more into the details. Did you check that on Canvas? Okay. I think you're not new to school. You're you're aware how Canvas works. I've uploaded everything into files. You could also see the materials, the syllabus, and everything through the modules. So I've uploaded here chapter 1, which is the introduction of power systems in general. And here you could see the syllabus. Okay. So we'll be having this course on Monday, Wednesday, and Fridays at this room. Also, we have an online section for our Springfield students. Primarily, we'll be doing this here in class. So when we were setting up the course, they asked me if I'd like to limit everything on Zoom for the online section, like the recordings and stuff like that. But I decided to keep it open for in-class students so that you could review or go over the recordings whenever needed. So this is actually a good advantage because primarily if we had just one in-class section, we'll not be doing recordings and stuff like that. So we'll have also a grader. His name is Seshan. You could see here his contact information, primarily his email. So anything related to assignments or grading, feel free to reach out to him to ask him about your grade or what's wrong with your assignment. Because I hired him because it will be hard for me to grade all your stuff on time and be aware of everything. I'll be still taking a look about the overall performance of the class. So if things do not resolve with session or you feel there's something wrong with that, feel free to reach out to me and I can tell him to do what's supposed to happen. So power system design and analysis, this is the course name. It's primarily a first course in power systems. So if you're not that interested into the topic or you don't know much about power system, this is the place to start. It's a 3 credits course. I don't really need to iterate that. So primarily, this course is covering some fundamentals of power systems related to balanced, unbalanced systems, power transformers, some stuff about transmission lines, and power flow analysis. So that would be primarily about like 6 chapters. I'll go later over the textbook. So in this class, we don't have a lab component, but I know the guy who teaches in the lab, and I'm aware that they include like couple experiments about certain simulator. So I'd like to include some simulation, even though it's not required for me to put it in this class, but I'd like you to have some exposure to some simulation within the course, at least to see how things really work out in industry, because I know many of you might be applying for internships in the field. And the first question would be, other than what type of coursework did you have in the past related to power systems, they would ask if you have any practical experience in any simulation software related to power systems. So having some exposure is very important, I think. So there's a simulator which is associated with the book. It's called Power World. It's not the best on market. It's primarily used for educational purposes, but everything you need, you could find it there. The big commercial software, which is you can buy for like $12,000 a license or $20,000, it has the same functions, but instead of 10 bus system, you could extend your system to 200 buses or 1,000 buses. So typically, if you get hired by any power company, you will have access to some software like ETAP or ESSE or similar stuff. So because those licenses really cost a lot, and we just have this one, which is available for free at least. So after you are done with this course, you should be able to understand the fundamentals of power systems, power system representation and its components, to be able to analyze the balanced and unbalanced systems, to perform some steady-state transmission analysis of transmission lines, and to be able to be aware, at least, to use and to understand the power system analysis software. Actually, the university sent me, or the university store, they sent me multiple emails, maybe 10 of them, to select a book for the course. And that means if I made that selection, you'll be required to buy it. But that would cost like $340 or so. So I did not really like to enforce the students to buy this book, even though it's very helpful. Almost half of it, like 360 pages, will be covered in this class. I'm not sure if I'll be able to cover all that in details, but there are a lot of cases you could go through if you are interested in the topic. And the rest of the topics, they are covered in the other class, which is Power System Engineering, 5540. So they would cover the rest of the topics. Actually, some of them, not even all of them. So I think this is a very good book, and it comes with that free license, so you could do your trials on your own. There are some solved simulations or already built there. You could just run and observe what's going on. The bad thing is that the university has some policy on the software which is running on its systems, and they do not include every software around. Like if I'd like to have this software, I'll go into a process with IT for a couple months to get that just approved to run stuff here. They are very worried about the privacy and the security of their systems. So that prevents us actually from running the software on the university labs or here even. But even though this is still fine because you'll have the materials ready to run on your own device. I can share with you some screenshots and maybe some recording, how that would work out. I'd provide some additional references. Actually, I got those 3 books also, and they are pretty amazing. Very new, up to date with everything you need. Those 2 concentrate, each one of them, on transmission or distribution. So in your future career, you won't be doing all power system related stuff. Mainly, you'll be concentrating on specific area, which is transmission, if you do like transmission planning related stuff, or distribution, which is more related to utility work. So those books are really well detailed, and I would suggest for the department to redesign the courses to make a course specific for distribution and a course specific for transmission, because the topics really vary widely. And it will give much more strength for the graduates and much more understanding of the related topics for each field. The third one is electric power systems with renewables. This makes some addition for integrating the PVs and the wind energy and all that type of new renewable resources, which is getting very important right now because of the shift in energy trends. And another good thing about that, they include simulations using PSSE, which is a very commonly known commercial software of power systems. I would say like 70% of companies use that software, so it's really worth it. So if you have that interest, I would recommend checking those references, but I'm not really aware if they are available online on our university library system or so. I got physical books for that purpose. Regarding the course policies, attendance expectations. While you are expected to attend all classes and participate actively in discussions and in problem-solving sessions if we're doing some solving examples or so. And for participation expectations, the most important thing is the timely submission of assignments. So since a grader will be dealing with that, I don't want really him to be overwhelmed by 60 submission of you. on one day and then figure out that I'm still having problems with some people not submitting today. I understand that we might get into those situations from time to time, but not all the time. So I highly recommend that you start solving your assignments as soon as possible. And don't be like me. I normally begin like 9 p.m. if I have a submission at 12 a.m. and things get out messy sometimes. I understand that there might be some last moment event or incident that prevents you from making a single submission or so, but let's help the grader to start grading as soon as the assignment is due. So let's say I would normally give a week for the assignment. So let's say it's due by 1 p.m. on Friday. It means a grader should begin grading right after that, 1 p.m. If some people are still submitting until Monday or Tuesday, that would be really tough for me actually to submit the solution, because by a week or two, there could be another pending assignment in the system or on Canvas. So let's cooperate on that point. I'm not mentioning things related to penalties and stuff like that because I don't normally do it on assignments. So I'm looking into really strong commitment of everyone on that point. Regarding the usage of AI, I know AI has been very helpful to me, at least, on many things. We're not doing programming tasks in this course, so I don't really recommend you copy paste the questions into ChatGPT or so. While you can do it, but I don't guarantee the answer. But still, I really recommend that everyone to try to do your best on your own, because this is the only way that you'll learn the content. Otherwise, you might get an A, but if you don't know the materials, it's not really worth it. If you get to a job interview and you don't really know the difference between balanced and unbalanced systems, ChatGPT could take the credit for that, but not you. So I really recommend doing the work on your own, and don't be really worried about the grades. We are very flexible on grading. But cheating, like copying somebody's assignment or doing it together or stuff like that, might raise some alarms on Canvas when we check the similarity. I'm not planning to do so. I think everyone here is really aware of that point. So do the best that you can. And if you have some problem, reach out. I do have an office hour weekly. I chose that to be on Wednesday in the middle of the week. So if you're stuck somewhere, let me know. If there's something wrong with the assignment, let the grader know. He should assist you on that, or at least give you some notes or remarks about how to do the thing. Primarily, we're doing really simple stuff here in this class. In industry, they run like 1,000 bus system or 200 bus system. Here at most, you'll be solving 2 bus, 3 bus system on hand calculations, stuff like that. So it's not really that hard. And we really don't need an AI related materials to solve the problems. But in previous semesters, I've seen really weird things, and I had the ability actually to force withdraw some students from the class, because I've seen a person, for example, he copy pasted the 10 previous assignments from last year or so. Even there was a mistake on the solved assignment, he copied the error, and even though it was scratched, so that cannot be done without seeing the previous solution. I don't expect to see such situations here. Even with him, I gave him a chance to redo the whole assignment. So he did it, and he got graded, but he committed to not do that again. But according to the department rules, I was allowed to force withdraw him from the class and give him an F in the middle of the semester. But I did not utilize that option. For communication, the preferred method of contact is definitely email. I usually respond pretty fast to any request, and the feedback on assignment or the grade should be given within 7 days of submission. I'll make sure that the grader is doing that as fast as possible. In case of emergency, you'll be notified through Canvas. I'll make an announcement or send an email for everyone so that you'll be aware of what's going on. We could make some recording for another lecture or maybe cancel a class if something happens. And if I go somewhere for some conference, I'll make you aware ahead of that so that you don't come in, show up to the class, and I'm not there. Regarding course materials, so as I've said, we'll be covering the first 6 chapters of this book. This is actually a large amount of work in this class. So we'll be trying to do as much as we can to cover the most important things, and I'm quite confident that we are able to do it, because those topics will be really needed if you take more coursework in Power later. So at first, we'll get into the introduction. There's a chapter called Introduction. It primarily introduces the history of power systems and how did they evolve and what are the current trends in power, the technologies, the standards and stuff like that. So you won't be tested on those materials, actually. It's just some information. There are no assignment on chapter 1. For chapter 2, we'll be getting into some math there. We'll start with phasors, calculations. Do you know what's a phasor? What's a phasor? Can anyone tell me that? Yeah, but I understand, but the phasor itself, like, is it like a magnitude or there's something added to that? Okay, a phasor is
with an angle.
Yeah, that's it. So everything should be represented in a phasor nature, where you have a magnitude and you have an angle for that. So we'll make some transformations here and there to make sure voltage, current, powers, and everything is in that format. Here I'm just putting few topics in each course, but we'll be covering almost the whole course. But here just an overview about the topics in each section. So then we'll get into the instantaneous power calculations in different types of circuits. So there's something called average power, which is typically the consumption that we have. When we get into instantaneous calculations, we are involving the time. There's a time equation which involves current, voltage, or power calculation. Then we'll get into different types of power, which is the real, the active, and the reactive power. And we'll do some calculations on the power factor. If anybody know about the power factor triangle, did you see that before in some course? So why do you think the power factor is important? Or its usage? Does it matter on anything?
Depending on the jurisdiction, they might charge companies more for power factors.
So I understand, but what's the significance of a good power factor or high power factor or a low power factor? Definitely. This is the most important thing in power systems. They really want efficient systems so that all the generated power gets into useful power, not something not useful in the system. And to do that, we should have a high power factor, which is up to 1. So there'll be some things that we need to do on the system to ensure that our power factor is close to 1. Otherwise, most of the generated power will be as a loss. So we'll do a lot of calculations on power factor and power factor correction related stuff. And then the balanced 3-phase circuits. I'll not ask you too much questions right now. I'm just raising some awareness about the topics. So in power systems, we typically look into a balanced system. We don't see, would like to see unbalanced systems. Unbalances happen in case we have some fault or stuff like that. So the normal operation is to have a good in shape system with balanced components. And this is what we aim to. So we also learn how to make those calculations on the three-phase system, which is available everywhere. The third chapter will be dealing with transformers. Do you know what's the function of an add transformer in general? Okay, great. It's the AC or DC voltage. Okay, great. But why it's called power transformer? Yeah, the issue with power is that we are using transformers with high, big ratings. The instrument transformers are very small. They sense things in range of few amperes or so, or few volts. Those power transformers are really big equipment, and they are used in large substations along the grid. And their calculations are so important for the efficiency of the system. So we'll get into the equivalent circuit of those type of transformers, how we could represent them, their components in math, and make all those calculations of efficiency. And we discussed the issue of an ideal transformer. What could be an ideal transformer? A transformer with the minimum loss or no losses, maybe. This is quite fancy, but we could make some assumptions to receive that type of transformers. And then we'll discuss the per unit system. The per unit system is a universal method in order to normalize the grid. So because of all those big transformers here and there, 400 volt could be okay in this region, but 600 volt there could be a little amount of voltage, and 800 there could be something acceptable. But for me, if you tell me at that moment the voltage was 605, so it will be hard for me to know whether that 605 is harmful for the system or it's a normal value, because we have different measurements everywhere on the system and different outputs of each transformer. So using the per unit system, we will normalize everything between 0 and 1. So you'd be telling me at that moment the voltage was 1.01 per unit. So you'll transform that 605 volts into 1.01. At that moment, I would understand that the system voltage increased by 1%, and that would be acceptable. But for another place, 605 will be 1.2 or 1.3 per unit, which is 30% above the normal condition, which may not be acceptable. So the per unit system is very important. And did you take the electromechanics course with Dr. Kimball? I think he goes through those per unit systems. Did he go through over them? Because they are used in motors, generators, related stuff. So those could be very helpful. And then we'll get into the big structure, which is the three-phase. There are single-phase and there are three-phase transformers. Three-phase ones are those large transformers with three independent transformers all connected together. But their issue is that they have really complex connections and they have a phase shift problem. When you get from the primary into the secondary side, you're not just transforming the voltage value, you are affecting also the angle, because as we have said, that voltage has it's a phasor. Other than the magnitude, it does have an angle. So there'll be some phase shift when making voltage transformations over those three-phase transformers, and it's very important. So we'll get into those calculations. And then we will discuss the auto transformers, which is a typical transformer with one winding. The normal transformers we know, they have two windings, one for primary and the other one for secondary. But for an auto transformer, we'll just have one winding, which is being shared between the primary and secondary sections. Chapters 4 and 5 will be quite the core of this course. because they deal with transmission systems. In Chapter 4, we will be going over the design consideration of transmission lines, how they should be, what are their components, what about their parameters, their loadability, and many other things. So we'll get into the resistance, inductance, and capacitance of transmission lines and the shunt admittance. So as an introduction, a transmission line is typically represented as a resistive component plus an inductive component. This is the nature of the wires in the transmission line. But the structure, when you have a number of transmission lines in three-phase, their structure will govern those calculations and will make certain magnetic field and electric field. The electric field will be associated with the inductance, and the magnetic field will be associated with the capacitance, which gets generated between those different conductors. So there are too many design calculations to ensure we have the proper values for inductance and capacitance. Otherwise, you see a big loss over the transmission line, because during the transmission process, because of the inductive nature of transmission line, the first thing that we will encounter is a loss by the resistor. The resistor have a loss which is P equal Ri squared. And then we'll have the inductive effect, which might lead for a voltage drop. So let's say we'll begin with 110 voltage at the sending end. If things are not really good at the receiving end, the voltage will be 100 or 105. That sharp decrease, which is like 5%, could have really big impact on the devices that you use. The capacitance deals with leakage current and stuff like that. We don't really need any leakage happening at the transmission level. For Chapter 5, we'll get into the upper level of transmission lines. We're done with their parameters. Now we are dealing with them.
Professor Slayman. I'm not sure if you can hear me, but we cannot hear you on Zoom.
Can you hear me now?
Yeah.
Yeah, there we
Yeah,
go.
you're good. You're good now.
Thank you.
Okay, I did not change anything, by the way. Okay, so MSU guys, Springfield people, everyone online, at any moment, I see here a green light on the microphone, which makes me feel that you are hearing me. In any case, if I stop talking, send something in the chat. Actually, there are 11 messages. Oh, everyone is saying yes now. So anyhow, disturb me if you don't hear me, because I might be looking into the syllabus. I don't know what's happening in the chats.
Can you also pronounce your name for me, please?
Mohammed.
Gotcha. Are you Sleeman or Slayman?
Anyone. Both work.
Okay.
Okay, because it's not in English, so anyhow, it won't matter. Yeah, so please let me aware of that issue if you don't hear me. I'm really worried about that. So let's get back. When did you miss me? Or you stopped hearing me?
Maybe like
On
3 minutes ago.
Yeah, on which section? Power flow? Did you hear me talking about the power flow?
No, maybe not even on transmission lines.
Well, the transmission section is really large. It covers 2 chapters. The chapter 4, where we discuss the parameters of the transmission lines, their design, their structure. And in chapter 5, we'll do the steady state operation with transmission lines and different approximations for the short line and the medium line. And then we'll get into some topics related to the loading ability of transmission lines, maximum power flow, and stability. In chapter 6, we'll be using some mathematical methods. Did anyone take numerical analysis or stuff like that from math? Who? Okay. So we'll be using some mathematical methods in order to represent the grid as mathematical equations, and then we solve it for a simple number of iterations. Basically, using your hand, you will make at most 2 iterations, maybe, over a 2 or 3 bus system. If I give you like 5 bus system or 10, and I ask for 1 iteration, it might take you 24 hours to do it on hand. So this is not feasible. We'll just do the simple stuff in class. Everything complicated would be for the power system software or simulator. So typically, the Gauss-Seidel and Newton-Raphson, those are the most common methods. They operate in a different way. So we'll get different values even for the same problem. The fast decoupled and DC power flow makes some good assumptions to make the problem more simple and less computationally intensive. So we'll get over those methods too. Important dates. We'll have 2 midterms. Since our class sessions are 50-minute sessions, so I would need to do 2 midterms rather than 1, so that in case some of us don't do that much on the first midterm, they would have another chance on midterm 2. The final exam is set by the department. This is something I cannot change or I cannot modify. But the dates of the midterms, we could really discuss that later. I put some tentative dates here. My plan is to finish the first 3 chapters and then do midterm 1, then go over the 4 and 5 chapters, which are related to transmission lines, and then do midterm 2. Eventually, we'll have power flows in the last chapter, and then we'll do the final. So those dates really depend on the progress of the class. The material is really large, and I'm not sure how fast we can go through all that. So it depends on our pace and the understanding in the class. So I'll be trying to receive some feedback from you to know if I should accelerate or reverse the way that I'm doing it. Regarding the grading policies, we would have 40% of the total grade on homeworks, which is quite generous because we'll not have that much homeworks. I believe 5 chapters could give us like 5 homeworks, but be aware that some chapters are really big, so I might need to divide the assignment into 2 parts. Otherwise, you'll have like 15 questions or so by the end of the chapter. I'll be using the book. So by the end of each chapter, we have a list of questions that are closely related to the content of the text, of the explanation. So in most cases, the homeworks will be very similar to what we are doing in class for the textbook explanations. So going over the class notes would be quite enough to do all the homeworks and even the exams. For the midterms, it's 30% total, 15 on each, and the final exam counts for 30%. The grading scale is a typical one that you know, A, B, C, D, F, and the ranges are quite common. Don't really need to explain that much about them. And the rest are some policies and academic dishonesty and generative AI policy. Those are typical things I need you to be aware of. I hope that you have received them from different courses also, so you should be pretty aware. There are a number of great resources on campus, so I encourage everyone to take advantage of all those good resources we have at SNT. And I think this is all what I have right now. I still have about 10 minutes. I won't start with the chapter because I think we're good for today. We will begin with the introduction for the course or even to the book, which is called Introduction, on Friday. The slides are already there, so you could have a look over the content. It's some literature related to the history and the current state of power systems. But before you go, I'd like to make it clear that it will be hard for me to track your attendance. It's required, actually, whenever we have in-class section to track the attendance, and the department really likes to see you all on campus. I understand that there is an online section, but this is primarily for the at-a-distance students or MSU people. So I invite everyone to be active participant in this class and to attend this section. And I'll figure out a way to track your attendance. Primarily, I'm not willing to take attendance for every session. We have 3 sessions per week. If I need to run a paper in the class, we'll spend like 20 minutes each class just getting through 60 people. So we'll be doing that occasionally just to track your attendance and make sure everyone is attending. People who have issues can now really go. Drop this section and go to the online section. That would be really fine. But primarily the attendance will be for the people in class. I will not prevent, if I see now some person trying to attend the Zoom session, I will admit him. I will not drop him out. But the attendance policy requires your physical attendance. If you have any question for me or any concern, please feel free to share. I'd like to welcome any suggestion or recommendation. Questions?
Do we need the 7th edition of the book to know what the homework is? Will you post the homework?
I had a look at previous versions. I personally had the 4th edition. It's closely similar to this one. My main concern is that it's not about the content. The things that you'll be solving, it's almost the same in each version of those. They keep adding case studies and stuff like that up to date from version to another. My only concern is that there'll be a page difference. So if I would say page 205, it could be different on an older version. But the good thing about this book that they have different type of loans. You could loan a book, you could use an online loan, physical loan. It's available somewhere online for free. I'm not aware about the 7th edition, but the 6th edition, I've seen that before. I personally have another 4th edition at the home. So I think you could use an older edition, but let me show you here. To resolve the issue, I have this ebook. It's for me also. It came with the book. So each time, let's say on chapter 2, I'll try here. I cannot post this book on Canvas. I don't have the permission. Otherwise, the publisher will take me to court. So, but I can show you prior to the problem, the questions at least, so that you get aware if you are using an older version of the book, that this is the question that I need to solve. So I can really support on that issue, but I'm not eligible to upload this ebook to Canvas. And I did not force people to buy the book or to add it to your tuition or so. So I kept it open to everyone to explore available options regarding that. And as you can see, the questions are very simple. So when I say 10 problems, don't be really scared, because some of them, each one of them might take like 5 minutes to solve or so. Except when we get into large problems like those, so it gets a little more complicated. This is how it looks like in our World Simulator. So here you see couple buses, those black rectangle shapes, those are called buses. And you could see some transmission line, which is a feeder here, because it's where the power is being pumped from the source. It has certain resistance, which is 1 plus 2J. It's the omega L. And then you see the flow, the power flow. Those arrows are like a power flow. And here at this level, we have another bus of 13.8 kilovolt, and you could see those two structures. This looks to be as a capacitor, which means it could be some reactive power device. We use that for stability purposes to make sure we are generating some reactive power. We'll get into that later. And here, this type of shape, it looks like a load. We have a load here, which is 8 megawatt. You see up and down arrows. If you press on those on the power wall, you'll be adding your load or increasing to your load. And then you see everything here is changing on the system, those measurements. So typically we see here the source voltage at 14.98 kilovolt, but at the receiver level is 13.8 kilovolt. So this is a normal voltage drop from the source to the load. This is a typical example I just came through now. I think we're done for today. And just let me check if Zoom people have any question. Yes, no, yes, no. Okay.
I had a question.
Okay.
How are you planning to do exams for the Springfield section?
For Springfield people, they asked me if I'd like to have a class. I've selected there also a class. There's a room that you'll be required to get into during exams. I'm not aware so far if I'd like to make an open book or closed book exams, but anyhow, either way, you'll be required to do that in class, and everything will be announced ahead of time.
Okay, thanks.
Okay. Thank you. See you on Friday.